Hi and welcome to this Leaving Cert Higher Level Applied Maths video. Today we're going to look at projectiles. If you're just beginning with projectiles, there is a better ordinary level introduction video which I've linked in the description below. In this video, we're going to work through some more higher level concepts and higher level ideas with some examples from the higher level papers. We're going to look at the key ideas around projectile motion. We're going to talk a little bit about air resistance. We're going to bring in some trigonometric identities, which can be very helpful for working backwards to get our angle. And we're going to work through a few exam questions, both from the older course and the new course. So here are some projectile key ideas. These are the ones that you need to be very, very familiar with. You need to be able to work with it. Acceleration due to gravity is equal to 9.8 meters per second squared. Gravity only acts up and down, so along the y-axis. So it's only going to be in the y direction when we break the projectiles up. We always take acceleration due to gravity as negative. There's only one example of a question where it was fired downwards. If something is fired even horizontally, gravity is still taken as negative. There's no acceleration in the x direction. And as soon as we begin our question, we start with our VUAST, and there's some key things that won't change. So before you even start the question, we'll be able to fill in our acceleration in an x direction is 0. Our acceleration in a y direction will be minus 9.8 meters per second squared. Because there is no acceleration in the x direction, that means Vx will be equal to Ux. Just to be very, very clear, time is not a vector. Time does not have a direction, so that's why there is no subscript on time. Time is our linking variable. It's the piece that we'll be able to link our x and y direction through. So that's a really, really important one. For everything else, the x value and the y value will be different. Time, it has to be the same. So when given the initial angle as tan theta or theta equals tan inverse, I would say go straight to your little sketch if you need to, but work out sine and cos using our Pythagoras rather than getting an angle, because it's going to get messy. If they give it to you in that form, it should give you nice whole numbers when you work with it in this way. So resolving initial gravity, we get u, our initial velocity, is going to be u in the straight lines, which effectively is the magnitude of the initial velocity, which is the speed. It's the initial speed, cos of the angle I, plus the speed times sine of the angle j. That's always going to be the case. Get really, really good at resolving for your initial velocity. The maximum height will be sy when vy equals 0. Watch out if you're fired off a cliff, because this will only get you s, remember, is displacement. It will only displace you from the from the vertical point you were. If it goes down further, you need to add that in. Time to maximum height is your time when Vy equals 0. And then for your range is Sx. Okay, so range is the displacement in the x direction. We're talking about if it's projected from the ground, when it lands, it'll be Sy equals 0. If it's projected from a cliff, Sx equals Sx when Sy equals minus whatever the height of the cliff is. And a really, really important one, don't forget that speed is the magnitude of velocity. So if you ever want to get back and get your speed, you have to get your full velocity vector, the I and the j part, and then you can work a little bit of Pythagoras, this little formula we have from our vectors anyway, to get us our magnitude. So let's talk a little bit about air resistance. So air resistance is the opposing force exerted by air on a moving object. It increases with speed and depends on the shape, size, and surface of the object. So when a projectile moves through the air, it is slowed down by air resistance, which affects its horizontal component of motion. And although the effect of air resistance is often small, it becomes significant in certain situations and must be considered when trying to maximize the horizontal range of the particle. Now, this is the one we are more familiar with. We see this kind of air resistance. If something is simply falling through the air, we need this quite a lot when we're doing our differential equations. And we can work with air resistance with differential equations because, as it says, the air resistance is changing with speed. So it is variable. It is not a constant, which is what makes it so tricky. So some of the things that influence our air resistance, velocity, so there is a proportional relationship there. The cross-sectional area, so obviously the bigger the area, the more air resistance there are. There's something called a drag coefficient, so a measure of how streamlined the object is. And then air density will come to play as well. So air resistance primarily reduces the horizontal component of the projectile motion, which shortens its range. So we get something like this. So we have a lovely symmetrical quadratic and negative quadratic curve, a parabola, when we work with our numbers of there being, or our assumption that there is no acceleration in an x direction. However, in the real world, there will be a deceleration in the x direction due to air resistance, which creates this slight, it starts along the same path, but we can see it drops much, much quicker. So in order to minimize this effect, the lower angle of release will be better. So if you were to work with our assumptions, 45 degrees will maximize your range. So 45 degrees, because it's exactly halfway, we can do a little bit of calculus to prove that. You can use trigonometry to prove that. So 45 degrees will be like the optimal angle. However, bringing in air resistance, you can see these are all color coded. So our 40 degrees is green, but you actually end up going further with 20 degrees because the lower angle actually counteracts that air resistance a little bit better. So the force due to air resistance is proportional to the velocity of the object, which always acts in the opposite direction. When the drag force becomes significant, so a notable reduction in the maximum horizontal range is observed. So by understanding these factors, you can predict how air resistance will affect a projectile and adjust variables like angle, shape, and velocity to achieve desired outcomes in motion. Now, why are we even talking about this in a projectile situation? So back in 2023, we were given the brief here. In many sporting events, an object is projected with an initial speed, initial angle. The object then travels in a curved path before it lands. The object may be kicked, thrown, hit with a club or bat, or it may be that the projected object is a sports person themselves. To maximize their chance of success, the sports person may consider the speed and angle of the object's projection, as well as the object's interaction with any wind present and/or with the air as the object moves through it. So very much focusing on this idea of air resistance and how it would affect what we do. Because our modeling underpins everything we do in applied maths, it's really important for us to understand that when we do our questions, we have an assumption that we ignore air resistance. Now, have they asked about air resistance on a paper? Absolutely. So we've seen in the SEC ordinary level paper that was released before the first exam, question 4, part 6, it gave us a graph that predicted the path of the slitter when wind and air were ignored. And then they asked to then sketch what would it look like if we end up taking into account air resistance. So not wind, just air resistance. So again, we end up with something like this. And what I want to really iterate to you is the fact that it won't follow a normal quadratic curve. It is going to not be symmetrical. And we start off along the same path, but then we fall short. It won't go as high and it won't go as far. And that's what they're looking for. Do you have an understanding of how air resistance will impact what we do? Do you understand how air resistance has been ignored for our calculation? So it's worth mentioning, it's worth talking about, and it is something that possibly could come up. Could we be asked to work with it in a paper? Not in terms of a projectile, Again, we do see air resistance come up in our differential equation questions where something is falling through the air. So air resistance working simply up and down against gravity, which is much more straightforward to work with. But it's a nice thing to get us thinking about our assumptions and what we have already ignored when we do these questions.
So when we're looking at higher level questions, the main difference is going to be the use of trigonometry and algebra. So here are some really useful trigonometric identities that we need as we work through our projectiles questions. So the first one is one that you're probably familiar with from both maths and applied maths, and that's the tan of the angle is equal to sine over cos. The second one is one, again, you probably should be familiar with from your maths. Sine 2a is equal to 2 sine a cos a. And our last one is one that's a little bit trickier and we have to build it. So it's telling us that 1 over cos squared a is sec squared a, and that is equal to 1 plus tan squared a. So really what we're focusing on is replacing 1 over cos squared a with 1 plus tan squared a. So the first one is really straightforward. It's there on page 13. Tan A is sine A over cos A. Second one is on page 14. It's at the bottom. It's the double angle formula. So sine 2A is equal to 2 sine A cos A. The third one is a little bit different. So we have two bits of information on page 13 that we need to connect together. So sec A is 1 over cos A. Okay, so that's our first bit of information. The second one is sec squared A is 1 plus tan squared A. So really what we're saying here is 1 over cos A is equal to sec A. So by squaring both sides, we get 1 over cos squared A is equal to sec squared A. That's not fully in the log tables. We're deducing that based on the bit we do have. And then we're told that sec squared A is equal to 1 plus tan squared A, which in turn gives us what we will use for our final substitutions, which is 1 over cos squared A is equal to 1 plus tan squared A. And what we're basically going to try and do with that formula is replace everything with a tan to create a lovely quadratic that we can work with. So you'll see that in some of our questions. This is question 7 part A from the 2024 higher level paper. The type of question we have here is a two angle of projection. So Fiona plays camogie and wishes to improve her accuracy in scoring points. She stands at P, which is 35 meters in front of the goal line, and strikes the sliotar with initial velocity 20 meters per second at an angle of alpha to the horizontal. In order to successfully score a point, the sliotar must pass over the crossbar, which is 2.5 meters above the ground, as shown in the diagram. Okay. So we're asked to derive an expression in terms of alpha for the time taken for the sliotar to reach the goal line. So that diagram there is containing pretty much all our information that was given in the paragraph. So the first thing we're going to do is we're going to set up our table. So RVUAST, straight away I put in my acceleration. Acceleration is always 0 in an x direction and always minus 9.8 in the y direction. That is because everything we look at currently is going to be a horizontal plane. So we start filling in additional information. The next thing I'm going to do is I'm going to resolve my initial speed, so our initial velocity. So what that becomes is, if you want to break this into its i's and j's, it's your speed, which is u, cos times the angle I, plus the speed sine times the angle j. And that will always be true when the angle is given to us on the horizontal. If you want to go deeper into how we resolve that using numbers and to see it in more depth, I've linked the introduction ordinary level video in the description below. So let's fill in u, because we know that that was given as 20. So we get 20 cos alpha I plus 20 sine alpha j. So that comes in here. So 20 cos alpha here and 20 sine alpha here. The next thing I fill in is always v of x, because we know there's no acceleration. So v and u is going to be the same in our x direction. That will help us later on in the question if we're asked for velocity. So it's just a handy one to start filling in. So then, because we're working with the goal line, we're going to think of the slitter as hitting right here. So in terms of my path, let's see what's going to happen. So I'm going to go and land like there. So every bit of information we put in is for that. So SX, so the displacement next direction is 35, while in the y direction it's 2.5. And they've asked us to drive an expression in terms of alpha for the time taken for the slitter to reach the goal line. So basically what we're being asked for here is time. Don't worry about all that kind of algebraic piece. It's asking for the time taken. That's our main takeaway. So the time taken. And we're talking about reach the goal line, which basically we're talking in an x direction. So we're looking at the time using the information we have in an x direction. So that deriving expression in terms of alpha just means we're going to end up with something algebraic. We're not going to end up with a number. So we're going to approach this the same way we'd approach it if we did have all numbers. So that is looking at my information. The bit of information I want is t, and we're going to use s is equal to ut plus a half at squared. So s is equal to ut plus a half at squared. Let's fill in and solve for t. So 35 equals 20 cos alpha t plus a half times 0 t squared. That all disappears and we're left with t equals 35 divided by 20 cos alpha. And now we've done that. We have an expression for the time taken in terms of alpha. So part 2 then asks us to calculate the values, plural, of alpha such that the slitter hits the crossbar. So when it gets to that goal line, that it will be at a height of 2.5. So how is there two angles where that happens? So we're really looking at a scenario like this, where we're going to have two projectiles. One is projected up higher and one is lower, and they're both going to meet at the same point. So that point here on our graph represents the crossbar. So that is 35 meters across and 2.5 meters high. So we're looking for those two angles. Now, don't worry about the two angles, because the way we will work, we're going to end up with a quadratic and we're going to get two answers automatically. We just focus on working with the information we have, and you're going to see how this comes out and how we get to a trigonometric, how we use trigonometry and trigonometric identities to get us to a quadratic and to solve for our two answers. So here's all our information. I've just added my 35 over 20 cos alpha. Remember that time is the connector, so I also can put my time in here. So 20 cos alpha. So I'm not going to use my x direction because that's how I found time. So instead I'm going to use my y direction. So the only formula I can use that will work is going to be s equals ut plus a half at squared. And I fill in all the information, which is 2.5 equals 20 sine alpha t. Actually, instead of t, we're going to put in our 35 over 20 cos alpha plus a half a, which is minus 9.8, and t squared 35 over 20 cos alpha squared. So when you're doing these kind of questions, I strongly recommend splitting it out so that any numbers that aren't fractions, so whole numbers or letters or variables, are all in the top line, and then the bottom of our fractions are the line underneath. It'll just make it a little bit easier and clearer to see what's going on. When you're working, it's easy to make a mistake, especially if we don't write it properly. If you're throwing in just a half, it's not an issue, but here in particular, where we have time as a fraction with trigonometry, it's really, really important. So we're going to do a little bit of cleanup. In this first piece, I have 20 on the top and 20 on the bottom, which disappears. I then have sine alpha on the top and a cos alpha on the bottom. So I'm going to bring those together so we can see it a little bit better. So 2.5 equals, I'm going to pull my 35 out in front, and then I'm going to have sine alpha all over cos alpha. So I'm just pulling my trigonometry pieces together. So basically swapping where the sine and the 35 were. It's multiplication, so multiplication is commutative, order doesn't matter, so that's absolutely fine to do. For the other piece, what I'm going to do is I'm going to multiply my half by my minus 9.8, which gives me minus 4.9. And then we're going to square out that fraction. So squaring a fraction, we're squaring the top and squaring the bottom. So the top line becomes 1225 all over 20 squared, which is 400. And that's going to be cos squared alpha. Now, our first piece here, this is going to, sorry, let me find my highlighter. So my first piece here, the sine alpha over cos alpha, is going to change to tan. So when we're working, we're going to now say 2.5 is equal to 35 tan alpha. So what effectively we're trying to do here is, although we only have one unknown, our alpha, we do have it with sine and with cos, and that's going to be a bit more complicated to work with because we have two different functions. So what we're going to do instead is we're going to change everything there to tan, which means we're going to have one single function and it's going to be easier to work with. For the next piece, what I'm going to do is in my calculator, I'm going to calculate my 4.9 times 1225 all over 400, and I'm going to leave the cos squared where it is. So that's 4.9 times 1225, and then divide that by 400. We can leave that as a decimal or as a fraction. It's up to you. I'm going to put it as a decimal just for space, 15.00625, and that's going to be times 1 over cos squared alpha. So cos squared is still in the bottom line. Okay, so it's still in the bottom line. Just be careful with that. But we now know we have 1 over cos squared alpha, and using the idea that 1 over cos alpha is the same as sec alpha, so 1 over cos squared alpha is sec squared alpha, we can now replace this so it's in terms of t. So that's going to give us 2.5 is equal to 35 tan alpha minus 15.00625 times 1 plus tan squared alpha. So that is a combination of two different identities that can be found on page 13. Make sure you're familiar with it. This feels like a really strange, weird thing to do, but actually all of these questions are going to work the exact same way. So once you've done one and you've done a bit of practice on them, then you'll find that actually they're all the same. And there's so many questions from our old course that are like this that you can practice. And I've left a link below with the document which gives you all the older questions that are still relevant and where you can practice a few of these. So what we have here is effectively a quadratic is a quadratic equation. Most students will be much quicker if they replace the tan alpha with x, just because our brains are better at working in terms of x. You don't have to, but I strongly recommend if you want to save time, even if you are a top student, it does save time. Your brain doesn't have to do as much thinking. It's a little bit more natural. So then tan squared alpha is x squared, and then we can work this through without any big issues. So we're able to go from there. So let's multiply this out. So 2.5 equals 35x minus 15.00625 minus 15.00625x squared. Bringing everything to one side, 15.00625x squared minus 35x, and then that's going to be 17. Oh, sorry, that should be plus 17.50625 equals 0. and then we go to minus b. So we're going to get our two values of x. So our two answers are 1.6059 and 0.7264. But remember, this is tan alpha is 1.6059 and tan alpha is equal to 0.7264. And that way, if you actually want alpha, we have to do tan inverse of first 1.6059. That gives us our first value of alpha as 58.09 degrees rounded to two decimal places. And then our second alpha is going to be the tan inverse of 0.7264. And that gives us 35.995 degrees rounded to three decimal places. So there are two answers there. So our two values of alpha. So a bit of a strange question if you've never seen it or worked with it before, but if you do a few of these, you will really find that they are the same. This is question 8 from the 2023 higher level paper. So two balls P and Q are projected into the air from points A and B, which are a distance d apart along the horizontal y-axis. The motion of the balls may be modeled as projectile motion in a vertical plane, ignoring the effects of air resistance. P is projected from point A at t equals 0 with initial velocity 38 and 41 degrees to AB, and Q is projected from point B at a time t equals 1 second with initial velocity u at 64 degrees to BA. So these two bits of information are super important, in particular that t equals 1, and we also have u and the angle for each. So the particles P and Q collide mid-air when t is equal to 3 seconds. So the first thing I'm going to do is I'm going to fill in our little tables for both A and B. So the first thing I'm filling in, and it's already there, is my acceleration, because that does not change. The second thing is going to be my initial velocity. So the initial velocity of A has a speed, of P, has a speed of 38. So it's going to be 38, and it's cos of the angle I plus 38 sine of the angle J. So I'm actually not even going to convert those. I'm going to leave them as is, but we can turn them into decimals if you like. That's absolutely fine. So 41 and then 38 cos 41 here. So we know they collide after 3 seconds. So I'm going to add 3 into my time here. So that's kind of all the information I have for P. Then for Q, I can do its initial, so I'm going to label that P and U of Q. Its initial is U, so we don't know it, cos of 64 degrees I plus U sine 64 degrees J. Now, you might think, okay, but I'm going to the left, so should we make it a negative I? And you'll be absolutely right in thinking, yes, usually to the left we would make it a negative I. But here's the thing about projectiles. When you're working with a projectile, if it's moving to the left or the right, is very much based on where you stand. It is very much which way you're looking at it. So from the other side, somebody will be looking at it. It is moving to their right, even though we're looking at it moving to its left. You can absolutely put it in as negative. There is no issue with that at all. However, it is going to make it a little bit trickier to work with the question because we're going to be adding and combining information from the right and the left. So if one is negative, we just have to be really mindful of our signs. So it's actually just much easier just to leave it exactly as this is. So we have U cos 64. Again, we know the time. However, we know Q is projected when T is 1. So this is going to be 3 minus 1, which gives us our 2. So just be careful with that timing piece. So we want to show that For part 1, u equals 28. Now, we don't have enough information in any of this, so we need to think about, well, how are we connecting them? So we're looking at the time when they collide. So what will be the same when they collide? So if you will think about that, the thing that's going to be equal when they collide is their height in the air, not their horizontal distance, because I don't know where they hit. They could hit maybe like here, they could hit here. We don't know where they hit, but when they hit, they definitely have to be at the same height. So the SY is going to be the same. So I'm just going to call that X for both, so we have a way to connect them. So I'm going to work out for each of them S equals UT plus a half AT squared. So S equal to UT plus a half AT squared. So that gives us for P, X equals U T plus a half minus 9 and we know T is 3, and 9.83 squared. And then for the Q, X is equal to U times T, which is 2 plus a half times minus 9.82 squared, and they are going to be equal. So we can put those equal to each other. So that's going to be 114 sine 41 minus 44.1. So that's P cleaned up is equal to 2u sine 64 minus 19.6. So we're going to isolate that u. So u is multiplied by 2 sine 64, and that's going to equal 114 sine 41 minus 44.1 plus 19.6. So that's going to give us u times 2 sine 64 equals, and it's about 77.9625. We're going to divide that then by 2 sine 64. No, sorry, that is actually 50.2907, and then we're going to divide that by 2 sine 64, and that gives us u equals 27.976, which is our approximate 28 meters per second, which is what they asked. So I've just updated my table for Q to include that 28, so instead of U. But again, I've left it in trigonometry if you want to change that to decimals, that's absolutely fine. And we're being asked to calculate the value of D, which is the distance between A and B. Now, what we know is going to happen is D is going to be a total of the displacement that P travels and Q travels when they collide. So really what we're saying is we need to add together Sx of both, and then we'll have our answers. So Sx for P plus Sx for Q is going to equal that D. So S is equal to, we're going to use our formula, S is equal to UT plus a half AT squared. We're working in the X direction. So we have S is equal to U, so 38 cos 41 times T, which is 3, plus a half AT squared, that's all going to disappear, plus our S for X for Q, which is 28 cos 64 times 2 plus a half times 0, 2 squared, which again, that's gone. So we're just adding those two pieces together. That is 86.04 plus 24.53 and that's going to give us 110.57 meters. So if they haven't told you how to round it, don't worry about your rounding. Just make sure you're not rounding it too much. So 1 decimal place, 2 decimal place, 3 decimal places, absolutely fine there. So part 3 has asked us to find, in terms of I and J, the velocity of P and the velocity of Q when they collide. So what we want to work with here is we want to understand our V in the I direction, which we have, but our V in our Y direction, which we need. And then same for here. So what we're going to do, we're going to use V equals U plus AT in the Y direction to find it. So V is equal to 38 sine 41 plus minus 9.8 times 3. And that's going to give us our V, which is minus 4.47. And then working with Q, V is equal to U plus AT. V is equal to here, U, which is 28 sine 64 plus minus 9.8 times 2. And that's going to give us 5.55. Now, because we're starting to talk in terms of vectors, we need to be very clear now about what we're working with. So if I go back to my diagram and draw in my I and my J axis, we can see that the vector for P is going up and to the right initially, and where we're catching it is when it's on its way down. Okay, so that is absolutely perfect. So what we're working with here for the velocity of P is going to be 38 cos 41, which, let me write down 38 cos 41I minus 4.47J. Now let's turn that into a number. So that's 28.68I. And then minus 4.47J. So that's perfect. Now, for the velocity of Q, we need to remember that to simplify our question earlier, we took to the left as being positive. But if we're working as true vectors, we need to put in the correct sign, meaning these should have been a negative. And then displacement in theory should have been a negative. And we should have looked at the minus there. So when we put this together, we're going to have minus 28 cos 64 I plus 5.55J. So what that ends up giving us is minus 12.27I plus 5.55J, just from a vector point of view. Even though we weren't too worried about it for earlier on in the question, now we start talking in terms of vectors, I's and J's, it becomes really, really relevant. As we're working with our own formulas, we can work a little bit differently. We can make life as easy as possible for ourselves. If you think you would find it easier to just put in the negative from the start, that's absolutely fine. So part 4 asks us to get the dot product. So let's just make sure we have our vector. So there's our VP is equal to 28.68 I minus 4.47 J. The velocity of Q is equal to minus 12.27 I plus 5.55 J. The dot product is going to be the velocity of P times the velocity of Q, and that's going to be multiplying our I parts together. We don't put in our I, so minus 12.27 plus our J parts minus 4.47 times 5.55, and then getting our answer, which is minus 376.71. So that is our answer for IV, and then hence or otherwise calculate the acute angle between them. So we need to extend that formula. So you have a formula in your log tables on page 17 at the bottom that we can work with. If you need to go back over that, I'd suggest looking at the vectors video, which is linked below. But basically what we have is the cos of the angle between two vectors is equal to the dot product. So in this case, VP multiplied by VQ all over the modulus or magnitude of VP times the magnitude of VQ. So that gives us cos of the angle is equal to dot product 376.71 all over. Now, if you want to get your magnitude separately, that's absolutely fine. We're working with the square root of 28.68 squared plus minus 4.47 squared, and that gives us about 29.03. Doing the same thing for Q, works out it's 13.47. So we get 29.03 times 13.47, and then we work backwards to get our angle theta using cos inverse. Actually just write a cos, sorry. So cos of this, it works out as negative, and that's fine. It's telling us it's an obtuse angle. In terms of our unit circle, think about we're in the second quadrant, and we end up with 164.44 degrees. They specifically asked us for the acute angle, so that means we have to take it away from 180 to figure out, well, think of what we have here. If you have two lines meeting, we have an obtuse angle, which is what we found, and we wanted to get instead the little acute angle. So we're going to take that away from this, so the acute angle is going to equal to 15.56 degrees. So quite a little tricky question. Not that anything was terribly difficult, but there was a lot going on there that you had to keep in mind, especially the vectors piece. So this is question 4, part A from the SEC sample higher level paper. A ball is projected from a point on horizontal ground with initial speed u at an angle alpha to the horizontal. The ball reaches a maximum height of h0 above the horizontal. Upon landing, the ball bounces with a maximum height of h1. The coefficient of restitution between the ball and the ground is e. Calculate h0 divided by h1. So there isn't a lot of numbers going on in this question, but we're going to just focus on each individual part before putting it together in the fraction. So we're going to calculate our h0. So first thing I'm going to do is I'm going to resolve my initial initial velocity. So this is going to be u cos alpha and u sine alpha, and we get u cos alpha here too. H0 is the maximum height. Maximum height is Sy when Vy equals 0. Okay, so that's really important. So our max height is Sy when Vy equals 0. What that means is it's the displacement in a vertical direction when it stops momentarily, but it only stops in the vertical direction. So there is no acceleration in the in the x direction, so there's no change there. So it's only in the y direction. So we're going to work with our v squared equals u squared plus 2as. U squared plus 2as to work out our h0. So u sine alpha all to be squared plus 2 times. We can leave this in terms of g if you want. It is fine either way. And we're going to rearrange this. So we get, 0 equals u squared sine squared alpha minus 19.6 h0. H0 then is going to be u squared sine squared alpha divided by our 19.6. Or if you prefer, and you've left it in terms of g, it's going to work out as over 2g. So then there is a bounce. Okay, so after we've worked in our first projectile, it comes down, hits the ground, and comes back up. So we have, and I'm going to label this the bounce. And in order to work with the bounce, we need to know the velocity before, and we need to know the velocity, well, we're going to then work out the velocity after. And we know the coefficient of restitution is E. So the first thing I need to understand is, well, how does it hit the ground? What is its velocity as it hits the ground? So I need to work out Vy. Remember, Vx is going to be the same throughout. So let's work out Vy, and then we're able to work with the bounce to figure out how the velocity at the start of the second bounce is. So really we're looking for the new initial velocity of that second bounce, of the second projectile after the bounce. So what we want is to find the velocity when it lands, and we're focusing on a y direction because we already know our x direction. When it lands, sy is 0, so we're looking for vy. So we're going to do v squared equals u squared plus 2as. So we need to take care with this formula, because when we work with it, we're going to have a square. So you're going to see what happens. Plus 2 times minus 9.8 times 0, which disappears. So we get v squared is equal to, I'm actually going to leave it as a bracket squared. Now, a very common error here will be simply to get rid of the squares or square root both sides, which is half correct. Think about where we are at. We're on the way down. So it's really important to understand that in a y direction, that velocity is negative. So what we really have is we have the plus minus square root of u sine alpha squared. That is fully correct. If we want to figure out the answers, there are two answers, because there's 2 points when sy is 0. There's the start and the end. At the start, it was a positive u sine alpha. So as it lands, because of its direction, it's going to be a negative u sine alpha. So that is our Vy. So just be really careful there with your signs. You might notice that it's actually the exact same as our initial velocity when it's landing. And that will always be true as long as we're projecting from the ground and landing on the ground. As long as we have that symmetry within our curve, we're happy. So it wouldn't happen if you're projecting it off a cliff, but it will happen in all scenarios that look like this. Our initial velocity in the y direction will be equal to the final velocity in the y direction, but they will be with different signs. They're going in opposite directions. So now let's think about the bounce. So what we have coming in here is, and I'm going to write it as a vector, u cos alpha I minus u sine alpha j. And then in terms of an impact, only one element is going to change. Now, if you look, our arrow's going down and then back up. They're both going to the right. So the only bit that's going to change is the j part. So only the j part is going to change, which means this vector here is going to be u cos alpha I still, but we need to figure out the new j part. So we can call that plus xj. And that's the bit that we're thinking about. So we're going to use Newton's law of restitution, and we have a formula in our log tables, which is v1 minus v2 is equal to minus e u1 minus u2. And we don't have a second particle because this is an impact. So it's hitting off the ground. You can think of it as the ground not having velocity. You can think of it as not having a second particle. So these elements disappear, which basically creates the formula. The new velocity is equal to minus e times the old velocity. And what we mean by that is x, our new velocity, is minus e times minus u sine alpha, and that gives us x is equal to eu sine alpha. So our new initial velocity for the second bounce is going to be u cos alpha I plus EU sine alpha j. So now we can work through our second bounce and find its greatest height. So we're on the second bounce now. We have our new initial velocities gone in, and we're trying to find Sy, which we're going to call H1, when Vy equals 0. So we're going to focus in a y direction, and we're going to use V squared equals U squared plus 2AS. So that is 0 squared equals EU sine alpha squared plus 2 times minus 9.8, or again, if you want to leave it in G, that's fine, H1. That gives us E squared U squared sine squared alpha minus 19.6 H1 equals 0. So H1 is going to be E squared U squared sine squared alpha all over 19.6, or if you're working in terms of G, that's going to be 2G. So then the question was calculate H0 divided by H1. So what we have for H0 is U squared sine squared alpha all over 19.6, or 2G. And that is all over, so that whole fraction is over E squared U squared sine squared alpha all over 19.6. You can see that there's quite a lot. This whole fraction piece is disappearing, leaving us with a 1 on top, and that gives us nice and simply 1 over E squared. So that's part one. But before we kind of move on to the second part, I just want to point out, if we have H0 divided by H1 is equal to 1 over E squared, we can create something a little bit nicer to think about, which is multiplying both sides by the denominators. I get H0 times E squared is equal to H1. And that's really helpful to understand. So basically what we're saying is the height of the second bounce, H1, is going to be H0, the initial maximum height, times E squared. So not just E, but E squared. And that's going to help us now with that second part. So the second part is the ball continues bouncing. Find an expression in terms of E and H0 for H5, the maximum height of the ball. So let me just kind of draw this out like a pattern, because it is a pattern. So there's H3 and specifically, well, a sequence. And we know that H0 is just H0. That's fine. We have now already said that, well, H1 is equal to, I'll put the E first, E squared H0. So because the coefficient of restitution is E, the second bounce, the maximum height of it, H1, is the original maximum height times E squared. And if then we bounced again, we're basically going to see the same thing happen. So we're going to see, okay, this is going to be E squared. So to get H2, it's going to be E squared times H1. But H1 is already E squared H0. So we're going to get E to the power of 4 H0. And we can continue. So this is a geometric sequence here. And we're trying to get to H5. So these are all E squareds. And we get E to the power of 6 H0. We get E to the power of 8 H0. And finally, E to the power of 10 H0. And that is the answer that they're looking at, or they're looking for. So H5 is equal to E to the power of 10 H0. It's a really nice question to highlight the relationships of the height of the bounce compared to just the speed. So when we're working with that coefficient of restitution, we're thinking of the fraction of that speed that's remaining. How does that impact the height? This is a lovely question that explores that. So this is question 3, part A from the 2021 higher level paper. So this is a question where we're generalizing the range. So we're going to be getting a formula for range that is true for all projectiles on a horizontal plane. So a particle is projected from point O with speed u at an angle alpha to the horizontal. Show that the range of the particle is u squared sine 2 alpha over g, and the maximum range from O to Q is u squared over g. So don't panic about the format or what way they've given you the answer. Focus on the fact that they've asked us to get the range. So we're going to work through this question just like we would any question. So I've set up my table and put in my acceleration. So next I'm going to put my initial velocity. In general, that's u cos alpha I plus u sine alpha j. So u cos alpha, u sine alpha, and we can also put u cos alpha into v. We're looking for the range. So the range is finding Sx, the horizontal distance, when it lands. So in this case, we're in Sy equals 0. So filling that in, I have a 0 here, and I'm effectively looking for my Sx. Now, how do we do that when we don't have enough information? We're actually going to work out our time here. So in the y direction, we're going to get our time, and then we're going to connect the x and y direction using that time. So in the y direction, we're going to start off with s equals ut plus a half at squared. So we have s, which is 0 because it's landed, u sine alpha t plus a half times minus 9.8 t squared. I'm actually going to leave this in terms of g in this question because there's a g in our answer, but you can take it back out at the end if you want. There's no issue. We're going to pull out a t, so think highest common factor, which leaves us with u sine alpha minus g over 2 t, and that all equals 0. So the times when the sy is at 0 is t equals 0 at the start, and then when we rearrange this, we get u sine alpha divided by g over 2, which is another way, if you think of u sine alpha divided by g over 2 is the same as multiplying by 2 over g. So this gives us, in a nice easier way to work with, 2u sine alpha all over g. So that's our time. So now that we have our t, so 2u sine alpha over g, we're going to find sx. So sx, so it's going to be ut plus a half at squared, which for us is going to be s is equal to u cos alpha times 2u sine alpha all over g. And the half at squared is going to disappear because the a is 0. And tidying that up, we get 2u squared cos alpha sine alpha all over g. That's not exactly what we want. You can see that they have changed that to a sine 2 alpha. If you go back to your log tables on page 14, we can see that 2 cos alpha sine alpha. So actually, what way it's written for us on the bottom page 14 is sine 2a is equal to 2 sine a cos a. So let me write that in so you have it. So it says sine 2a is equal to 2 sine a cos a. And now we can rearrange that into u squared sine 2a all over g. And what we've effectively found, sorry, that should be alpha. What we've effectively found is like a formula for the range. So that range is true for any projectile on a horizontal. We just have to fill in the relevant u and the relevant alpha. Now, I wouldn't suggest learning that off, either the longer one or the shortened version. But it is good to kind of practice some of these so if it did come up that you're very confident with it. Now, the second part of this, I'm just going to move up here where I have a little bit of space, is asking us for the maximum range. So the max happens when sine of an angle is equal to 1, because that's the biggest sine of the angle can be. So it doesn't matter that it's a double angle, it doesn't matter anything like that. The biggest value sine can be is 1. So then the max range is simply going to be what we have, but filling in 1 for sine. And that's what gives us our u squared over g. Now, if you want to go a step further, we can think about, well, okay, if we have sine 2 alpha and we're saying it's 1, that would give us 2 alpha is equal to the sine inverse of 1, which is 90 degrees, which gives us that alpha is actually 45 degrees. So that's a nice little idea that 45 degrees is what maximizes the range. But just remember that if we were to take air resistance into account, this kind of goes out the window. This is all when we're ignoring air resistance. So our assumption here is that there is no air resistance. So that's part 1. So if the angle of projection is increased to 60 degrees, the particle strikes the horizontal plane at P. Find the distance P to Q in terms of U. Now, we're not going to start this question again. We're really going to focus on the fact that the generalized formula for range for any projectile is this. So that means to get to get O to P, so to get the range when it lands at P, we're just simply going to put in our U, because it didn't give us U, but we are going to put in our 60 degrees. And that's all over G. So we have the sine of 120. That's over G, and that's root 3 over 2. So U squared over G, root 3. It is root 3 over 2 up here, but we can always tidy that up with the U squared and the root 3 on top, and then the 2 and the G on the bottom. Okay, so that is the same thing as having U squared over G times root 3 over 2. So you can kind of see it a little bit better that way. So that's O to P. So to get P to Q, we're simply going to do O to Q, which is the maximum range, minus O to P, which is the range we just worked out. So that's U squared over G minus U squared root 3 over 2G. I'm going to make a common denominator first, so throwing my 2's in there. And I'm going to pull out my U squared on top. That's 2 minus root 3 all over 2G. You don't need to clean it up exactly like that. You can tidy the whole number piece up if you want. And the number piece, if you tidy it up, is 0.014-ish. And that's absolutely fine as well if you don't want to leave it in terms of G. It didn't ask for it in terms of G. So this is question 3 part A from the 2019 higher level paper. This is where we're projecting a particle from a height. So a particle is projected with speed 40 meters per second from a point A on top of a vertical cliff of height 30 meters. The maximum height reached by the particle is 42 meters above the horizontal ground at point B. If it strikes the ground at C, find the value of alpha, the angle of projection, the horizontal range of the particle, and the speed of the particle as it hits the ground at C. So the first thing we're going to do, we're going to work with point B. So we're going to work right here. Now, when we're thinking about B, in our calculation to do the maximum height, we always look at S, the displacement from the point of projection. So this part here is SY when Vy equals 0. To get the max height, they've had to add on this extra 30 from the cliff, meaning that SY will be just calculated as 12. So when we're filling in this information, we need to bear that in mind. So just be really careful from anything projected on a height. So from point B, we're going to start with our initial velocity. So that's U. So we have 40 cos alpha I plus 40 sine alpha j. That's 40 cos alpha here, 40 sine alpha here, and that is 40 cos alpha here. Because the particle's greatest height. So at B, we know Vy is going to be 0, and we know that is going to give us 12. So we're going to work in the y direction because that's what we have most information for. So we're going to work with V squared equals u squared plus 2as. So v squared equals u squared plus 2as. This is all for part 1. So we have 0 squared equals 40 sine alpha squared plus 2 times minus 9.8 times 12. So 0 equals 1600 sine squared alpha minus 235.2. So rearranging that, we get sine squared alpha is equal to 235.2 divided by 1600, which gives us 1.47. We're going to square root both sides there, 0.147. So alpha is going to be the sine inverse of the square root of 0.147, and that gets us our angle, which is 22.5 degrees. So that's our part 1. For part 2, then we're talking about the horizontal range of the particle. So as soon as we start talking about the range, we want to change up what's going on in our VUAST table. So we'll take these out. And the horizontal range, so just to remind yourself, our range is Sx when it lands. So in this case, when it lands, Sy is negative 30. That's really important that it's a minus 30 because we're 30 meters below where we started. So we have minus 30 going in there. We're going to work out our time, and then we're going to plug our time in here, which will then in turn get us our Sx. So that's our range, always how we work with it. So we're going to use S equals ut plus a half at squared. So S equals ut plus a half at squared. We get S, which is minus 30, is equal to 40 sine, let's throw in our alpha, 22.5 degrees, t plus a half times minus 9.8 t squared. Let's do a little bit of cleanup on that. So 4.9 t squared. So we had a minus on the right. I brought that over to the left. Then we 40 sine 22.5 t. So that's going to be minus 15.307 t, and we still have our minus 30 equals 0. So we have a full quadratic here. So we're going to do our quadratic formula to figure out 2 different answers. Because of the way that we have a minus 30 there on the end, we're going to have the roots will have 2 different signs. So we are going to get a negative t, which we're going to ignore. So let's put that into minus b. So positive, the plus 1, we get 4.488. And then the minus is minus 1.36, but we're obviously ignoring that negative time. So that's the time when this particle lands. So we can throw that into the table, 4.488, 4.488. And then we're going to do our S equals, so let's get rid of all this so we can work with it. So we're going to work with our X direction. So we're going to do S equals ut plus a half at squared to find our range, plus a half at squared. That is Sx is equal to 40 cos 22.5 times 4.488 plus a half times 0 t squared, because that's all gone. I don't even need to sub it in. So what we're doing is 40 cos 22.5 times 4.488, which gives us our range of 165.85 meters. So if you want to round that up, so 0.9. So I've just filled in our table again with all the information we know at C. I've changed our U's from what we had, which was 40 cos alpha and 40 sine alpha, putting in our alpha at 22.5, so we have them as numbers. So part 3 is asking for the speed of the particle as it hits the ground at C. So what we're really being asked for first is to get the velocity vector. So the velocity vector is 36.955 I plus something j, but we don't know what that is. So we're going to work out our velocity in the y direction first. V is equal to u plus at. So that is going to be V is equal to 15.307 plus minus 9.8 times 4.488. And let's put that into our calculator, and we're getting minus 28.695. So that gives us minus 28.695 j, which is our velocity vector. They've asked us for speed, so speed is equal to the magnitude of velocity, which means we are looking at getting the magnitude of this vector, so 36.955 squared plus minus 28.695 squared, and when we do that, it works out as 46.79 meters per second. So very nice, straightforward question. Just don't forget what we know about our speed being the magnitude of velocity. So this is question 3A from the 2016 higher level paper, and it is an example of a question where we're seeing a projection downwards. So I'm going to set up my table here. A ball is thrown from a point A at a target T, which is on horizontal ground. The point A is 17.4 meters vertically above the point O on the ground. The ball is thrown from A with a speed of 25 meters per second at an angle 30 degrees below the horizontal. The distance OT is 21 meters. So we can see all of that happening on the diagram. The ball misses the target and hits the ground at the point B shown on the diagram. Find the time taken for the ball to travel from A to B, the distance from T to B, and the point C is on the path of the ball vertically below T. Find the speed of the ball at T. So there's quite a lot going on. So the first thing we're going to do, we're going to start filling in our table. So we're talking about going from A to B. So the few things that we know at B is that SY is going to be minus 17.4, which means it's going to be 17.4 meters vertically below where we started. So then I want to resolve my initial velocity. So my initial velocity is going to be 25 cos 30 degrees I. And then when we get to the J, this one's going to be negative. And the reason it's negative is because it's going downwards. So this very rarely happens in projectiles. We are going up, we get a positive J, but for us here, this is a negative J. And I would really take that into account when you are working. So then this gives us 25 root 3 over 2I minus 25 over 2j. So that gives me 25 root 3 over 2. This gives me 25 over 2. And this also gives me 25 root 3 over 2. So I'm trying to find the time taken for the ball to travel from A to B. So I'm just going to work in the y direction and figure out RT. So part 1, we're going to use S equals UT plus a half AT squared. So we get minus 17.4, and that minus is so important. I'm sorry, I should have a minus here for my 25 over 2. So minus 25 over 2 T plus a half minus 9.8 T squared. You might want to just multiply across by 2 to make it easier. So that would be minus 34.8 equals minus 25T minus 9.8t squared, rearranging that, 9.8 t squared plus 25t minus 34.8 equals 0. We now have a quadratic that we're going to solve. You're going to get two answers. You're going to get a positive and a negative. The positive answer is t equals 1, which is what we want. And the other answer is t equals minus 3.55, and we're going to ignore that. So the time taken to go from A to B is 1 second. So now I can connect both of those in the x and the y direction. It now wants us to find the distance from T to B. Now T to B is just this little part here, but what we're going to do is we're going to say, well, if you want to find T to B, we're going to first get O to B and then take away O to T, which we know is 21. So really we're asking from O to B, which is the range. So we're looking for SX. Okay, so the range when it lands is equal to SX. I'm sorry, no. So the range is OB in this case. So we're getting SX when it lands, which is when SY is minus 17.4. But we've already got that when SY is equal to minus 17.4, because that is when T equals 1. We've already worked that out. So we're just getting our SX. So we're going to use S equals UT plus a half AT squared. And we're going to say S is equal to 25 root 3 over 2 times 1 plus a half times minus 9.8 times 1 squared. And that's lovely and straightforward. Straight into the calculator, and it gives us 21.65. And remembering that's OB. So if we want the length of T to be, we're going to take that number, 21.65, take away our 21, and we're left with 0.65 meters. So looking at part 3, the point C is on the path of the ball vertically above T. Find the speed of the ball at C. So what we're looking for is we want the velocity vector, but we need to understand, well, what information do we know about C? Now we don't know its height. But what we do know is its horizontal position is going to be the same as T, which means when we look at SX, we're talking about this being 21 meters as well. Now, we're being asked to find the speed, which means I need to find two bits of information, which is Vx, which we already have, and Vy, which we need to work out. So I need a piece of information to work in the y direction, which I don't have. So what I'm going to do is we're going to look for T using the information we have in the x direction and connect that. And once we have the T, we're then going to work out V. So a two-step process. Remember, time is our connector. So in the x direction, to figure out our T, we're going to use S equals UT plus a half AT squared. We have 21 is equal to 25 root 3 over 2t plus a half times 0t squared, which all disappears. So t is 21 divided by 25 root 3 over 2. And that's easier to put in your calculator compared to a complex fraction. So that gives us 0.97. So that's our time it takes to get to that horizontal position, which means that's the time it takes to get to C. I can now plug my T in there and I'm going to get my velocity vector V, but I need the V in the y direction. I'm going to use V is equal to U plus AT. So that gives me V equals remember we are minus 25 over 2 plus minus 9.8 times 0.97. So the velocity in the y direction is going to give us 22.01. And if we want to turn the 25 root 3 all over 2 into a decimal, that's about 21.65. So that gives us the velocity vector of 21.65 I. And sorry, that should be at minus 2201 and then minus 22.01j because we're still moving downwards. And then the final step is they asked us for speed. So speed is equal to the magnitude of velocity, which means we're going to do the square root of 21.65 squared plus minus 22.01 squared. And when we do that, we get 30.87 meters per second. So a little bit of work in that part. It might seem like straightforward if they're just asking for speed, but there's quite a lot of elements to that. Just be very careful with that projection downwards. Really focus on how that's named. This is question 3, part A from the 2006 higher level paper. A particle is projected from a point O with velocity 9.8 I plus 29.4 j, where I and j are unit perpendicular vectors in the horizontal and vertical directions, respectively. Express the velocity and displacement of the particle after t seconds in terms of i's and j's. So we're going to work with position vectors here and a little bit of algebra, so working in terms of t. So anytime they ask for a vector, really all we're working with is in each direction getting the x and the y component and putting them together. So the first thing I'm going to do is I'm going to look at my initial velocity. Lucky for us, we don't even need to resolve it in this question because they have given it to us. So it's 29.4. I can put my 9.8 there as well. So we're doing everything in terms of t. So the two things they ask is for, first of all, the velocity vector. So the velocity vector, all we have to focus on is getting Vy, and we're going to get that with u plus at. So that means V is equal to 29.4 plus minus 9.8 times t. So it gives us, rather than a number, an expression, so 9.8t. So then my velocity vector, so I'll put this in here, 29.4 minus 9.8t. So my velocity vector is the I bit, which is 9.8i, plus 29.4 minus 9.8t, and that's your j component. So that's our velocity vector. The second then is our displacement vector. So I'm going to still use my s for this. So we want the s vector, which is sx and sy, neither of which we have. Okay, so it's going to be the sxi plus syj. So let's work them both out using s is equal to ut plus a half at squared. So sx is going to be 9.8 times t plus a half times 0t squared, which disappears, leaving us with simply 9.8t. Lovely and straightforward. For sy, we have u, which is 29.4 t plus a half times minus 9.8 t squared. So that's going to give us 29.4 t minus 4.9 t squared. So 29.4 t minus 4.9 t squared. So our displacement vector is 9.8 ti plus 29.4 t minus 4.9 t squared j. So that's our answer to part I. So actually I'll move it down here. So our velocity vector and our displacement vector in terms of I and j after t seconds. So find in terms of t the direction in which the particle is moving after t seconds. So we already have from part 1 our displacement vector and our velocity vector. So when we talk about the direction we're moving, we're always talking about v because we're moving. So we have our v. Let me change to our other color. Actually, we have our v here, so I'll just work with what we have. So here's our v. So basically at any point we have a velocity vector like that. What we're being asked to do is find the direction. So for example, what is our angle? So what we're going to do for our velocity vector we're going to think of, there's my j, there's my I, so the tan of the angle is equal to the j over the I. So our tan of this angle is going to be the j, so 29.4 minus 9.8t all over 9.8. So the actual direction, we're going to use tan inverse 29.4 minus 9.8t all over 9.8. So this is the direction the particle is moving. Be really, really careful with this. We don't want this to be confused with the idea of displacement. Displacement is the position where you currently are, okay? But it doesn't give the direction you're moving. If you're talking about the direction you're moving, you're talking about RV. Now, that fraction can be tidied up slightly, so that 9.8 can actually be divided in. So we're going to do tan inverse, and we're going to get 3. So 29.4 divided by 9.8, it's 3 minus t. So that's much nicer and much simpler. And then part 3 asks us to find 2 times when the direction of the particle is at right angles to the line joining the particle to O. So we've just worked out the direction. That's fine. That's if we look at the diagram to kind of help us along here. We're talking about this part here. Oh, 1 second. So we're talking about this part here. So we've just worked that out in part 2. The line now that they've added in is this line here, and that is the direction for the placement. So really we're talking about its position. So we think of this as our S displacement vector. So we've already worked that out. So we have our S and our V. We also have the direction of V. So remember that was like tan inverse of 3 minus t. So that was the angle that it is moving in, or the direction it's moving in. So for V, we're going to do the same kind of thing. So let's call that angle alpha. So it's going to be the tan inverse of the J. So 29.4t minus 4.9 t squared all over 9.8t. Again, we can do just a little bit of cleanup on this, and it works out as 3 minus a half t, and that's our angle alpha. So we want these two to be at right angles to each other. So the easiest way to do this is to remember that tan of any angle is equal to slope. So we could have the tan of theta is equal to 3 minus t. We have the tan of alpha is 3 minus a half t. We can think of this as slope 1. We can think of this as slope 2. If they're perpendicular, slope 1 multiplied by slope 2 should give us minus 1. So by working it that way, we simply get 3 minus t times 3 minus a half t, and that should equal minus 1. And then working that out, we get 9 minus 3t minus 3 over 2t plus a half t squared equals minus 1. If you want to tidy that up and multiply across by 2, might make life a bit easier for you. So minus 3t minus 3 over 2t, that's minus 9 over 2t. Multiply that by 2, we get minus 9t. And then we get plus 20 equals 0. And then we can actually solve that very, very quickly with factorization. So t minus 5, t minus 4. So our times are 5 and 4. So a nice kind of way to approach this. You can think about the angle between them as being 90 degrees and use some deeper trigonometric identities here. That will also work, but slopes are the nicest, neatest way that we can work. So we could do part 3 using the dot product. So here's our 2 vectors, and this is from page 17 of your log tables. So when this question was asked, dot products were not on the course. So trigonometry was really the only way to approach it. I do think trigonometry is definitely easier in this question. It's been set up in such a way that to make that easier. So this is probably not the best method to work forward, but if your brain straight away goes to it, I want you to see maybe how it still can work. So what we would say is when we do the dot product of S and V, it will equal 0, because that will happen when we have two vectors perpendicular to each other. So when we have S perpendicular to V, which basically means right angles. So what we're going to do is we're going to multiply our 9.8t by 9.8, so the i's by the i's, plus the j's 29.4t minus 4.9t squared times 29.4 minus 9.8t, and multiply those together, and we get 96.04t. 29.4 by 29.4 t by 29.4, that gives us plus 864.36 t. So then we have minus 4.9 t squared by 29.4, so that gives us minus 144.06 t squared. So all I've done there is this by this and then this by this. And then we're going to do it the other way, which means we're going to multiply these together and this together. So we have, so I've done this, yes. So I've multiplied these two together, that gives us our 864.36 t. And then these together, which gives us our minus 144.06 t squared. So now I'm going to multiply this by this and this by this. So that's what we're multiplying. So if you need to split that out, absolutely do. So 29.4t by minus 9.8t is going to give me minus 288.12t squared, and then finally 4.9, 9.8, both of them negative, t squared by t gives us plus 48.02 t cubed, and that equals 0. Now, we have t to the power of 3, but we are going to be able to pull that out. So let's do a little bit of tidying up here. We have a t term, we have another t term, we have a t squared term here and a t squared term. I'm going to pull out my t at the same time. So I'm going to have t bracket, that's going to leave me with 48.02 t squared. When you add the two t squared terms together, we get minus 432.18. It was t squared, but I put out a t, so that's just t. And then the two numbers there together gives us plus 960.4, and that all equals 0. So one of our times is going to be t equals 0 from there, and then we use the quadratic formula to solve the quadratic, which gives us t equals 5 and t equals 3.99, which gives us the exact same times. So probably not as nice, the numbers are a little bit bigger, but if this is your preferred method, it will work. It will work to give us the same answers.